and you would have EX addition, like HCl would protonate and chlorine would trap, hydrochlorination, or you could have hydration, or you have bromination. Okay? That's addition. This guy behaves differently. Rather than the nucleophile coming in here and adding, the system realizes that by simply losing a proton, it's back to an aromatic ring. So it regains the full aromaticity of the starting guy. And so instead of adding, proton comes off. And it comes off, basically, it's plugged off by, remember, H plus doesn't exist in solution. It's plugged off by X minus or anything in the mixture solvent that has an electron pair and can solidate the H plus. So that's the divergence. So what is the potential energy diagram? Benzene starts out here. The reactions, of course, typically should be exothermic, otherwise they wouldn't occur and we wouldn't discuss them. So if you remember the analogy with this gizmo with buckets and water and connected by rubber tubing, this one would be an upper bucket, this is a lower bucket, lower in energy. And here's the connectors. Here are the connectors, the rubber tubing. And the issue is, we know we have an intermediate, right? So that was just the mechanism we wrote in the previous slide. The question is this transition state, where is this transition state relative to this one? And you can already predict this. This one should be clearly higher, so the first step should be relatively slow because we're killing benzene aromaticity. The second one should be really fast, and it is, because we're regenerating aromaticity. So you have this double hump mechanism where we go through a slow step, reach the intermediate very quickly depletes to product. There's no buildup of this or anything like that. Okay, so let's look at an example. Benzene can be brominated. Benzene turns into bromobenzene. First of all, you may ask, is this even exothermic? And you can look up, you can do these calculations yourself. I estimated -10 by just looking at your tables in chapter 3, where you have bond strength tables. You calculate what you're losing, which is a phenyl H bond, and you're losing a Br-Br bond, and what you're gaining is a phenyl Br bond and an HBr bond. And when you subtract what you gain from what you lose, you find out that overall you're gaining 10 kcal, so it's downhill by 10 kcal. Okay? That's sizable, perfectly good. Now, I'm saying we can brominate benzene, and just a minute ago I said you can't brominate benzene. Well, you can if you use another ingredient, a catalyst that activates the bromine with respect to electrophilic attack. And that catalyst is a Lewis acid. The most popular is iron-free tribromide. It's readily made. It's actually often added in the form of iron filings to the reaction mixture, just a few of them. They immediately react with bromine to make FeBr3. FeBr3 itself, you could use that, but it's corrosive, hygroscopic, hydrolyzes quickly in air, makes HBr, it's a mess. So iron filings is just iron metal. So you're generating that in situ in your pot. And that's the magic ingredient that spiffies up the electrophilic power of bromine. And the mechanism is shown up there, but I'll do it slowly on the board, the low-tech version. How does it activate bromine? Now, Lewis acid is characterized by the fact that it's electron deficient. Okay? It's typically a sextet. So you can think of this iron as an electron sextet. We've learned about a bunch of Lewis acids. BF3, aluminum trichloride, aluminum tribromide, and the like. They're all electron deficient, so they're dying to find an electron pair. And so this guy, faced with this guy, will go right in and grab this electron pair. So when you do that, you get a new beast, which contains now a much more electrophilic bromine end. So remember the simple rules. You always start your arrow at the electron pair, move towards the electron deficient species, and when you're done, the origin, the locus of the origin of the electron pair always goes up one charge to positive. Okay? So in this case, it's full plus. If you started with minus, it would become neutral, and so on. Okay? And the recipient, of course, goes up in a negative charge. Okay? So here we now have plus here, minus here. And you can either look at this and say, okay, now this positively charged bromine pulls on this electron pair that links it to the second bromine, making this highly delta plus. That's where you have now a much hotter bromine, electrophilic bromine. Or you can illustrate that in another resonance form, where you take this electron pair and move it in, making this a double bond. No, that's not what I want. You want to move this electron pair towards this bromine because this is the positively charged bromine. So you have a double bond here. And that puts the plus charge on the terminal bromine, which is another way of illustrating that this bromine is much hotter electrophile than the originally not dipolar, equal charge on left and right bromine. And then this guy is hot enough to undergo electrophilic substitution or electrophilic attack. And so this double bond attacks here, this electron pair moves up here, and this becomes a leaving group in this process. So it's like an SN2. Or if you want, you can think of this as just the first step of the electrophilic bromination of an ordinary double bond with bromine. Remember that worked by making a cyclic bromonium ion. The double bond attacked a now positively polarizing in the transition state Br-Br bond, where this became delta plus and this delta minus. Eventually this took off as Br minus. Now we have a much better leaving group, and so this is a much hotter delta plus. So the Br minus has been modified to include the iron, so it's FeBr4 minus. And here we have two more resonance forms, and the counter ion is FeBr4 minus. Let's draw it still with one bromine dangling like that. Because we then grab this bromine in the last step to regenerate the aromaticity of the system. And that gives you bromobenzene plus HBr plus you regenerate the catalyst. which goes back into the catalytic cycle, okay, like that. Jumping the little hurdle here, going right there into the original equation. That's why FeBr3, you need only a pinch of it. Theoretically, only one molecule will turn over all the molecules of bromine to undergo electrophilic attack on benzene. And that finishes the reaction. So it's basically a modified halogenation of a double bond, modified both with respect to the reagent, which is this guy here, or the attacking species, which is this guy, and modified with respect to the last step, where it's deprotonation to regenerate the benzene ring rather than addition of Br- to the plus charge. That finishes that cycle. As I said, other Lewis acids will be catalytic. Typically, what you try to use is, if you're doing a halogenation, is to use a salt, a Lewis acid with a negatively charged ion that is the same as the attacking species. So we have bromine and bromine. And this is simply as a precaution because sometimes there's exchange. So you don't want to use iron trichloride, even though in principle it should work because there may be exchange between chlorine and bromine, and then you get chlorine showing up in your product. You don't want that. So to safeguard this, you do this. But other Lewis acids in principle work. We will see Lewis acids as activators all over the place. Lewis acids are perfect in activating a haloalkane or an alcohol and the like by attaching themselves to the electron pair and then starting to pull on that bond, trying to rip that guy off to leave behind a positive charge. Yeah?
Sorry, why did you say iron chloride was not okay?
Because you get exchange between bromine and chlorine. And so suddenly you'll have BrCl in there instead of Br2 and that kind of stuff. And that will give you chlorobenzene a few percent, and it'll make your product impure. So you want to avoid that, yeah. All right, so number 2 is nitration, but before we do that, let's have a break. You mean my voice isn't blaring enough? It usually is. Thanks. So there's a second reaction that's also extremely useful because it introduces nitrogen. And nitrogen is about 85% of physiologically active compounds. This is a very rough guess. Certainly of medicinally important molecules, drugs, contain nitrogen. Okay, so it's a very important atom in physiological activity. It's because of that lone pair that's sticking there in amines. It's basic, and it can form hydrogen bonds and so on. So in nature, that's exploited to the hilt. So synthetically, that's a very important transformation. And it basically uses nitric acid. But nitric acid and benzene don't react, or too slow. So what you do is you spiffy up nitric acid to be a hotter electrophile by adding a pinch of consulfuric acid. So it's literally a drop of sulfuric acid to activate the nitric acid. And then what happens is you introduce nitro and you replace one of these protons again by electrophilic substitution. So what is nitric acid? Nitric acid is, you can look at it as a hydroxy nitrite. Okay, here's the structure again. Okay, and so in the presence of consulfuric acid, hydroxynitrite, which has already an electrophilic nitrogen sitting there because of the Lewis octet rule. If you go back to chapter 1, the nitro group is one of those funny guys where you have to write a dipolar structure to ensure Lewis octets. Okay? And so that puts a plus charge on nitrogen and a negative charge on one of the oxygens. Of course, there's another resonance form where these two oxygens trade places. And so that makes this nitrogen electrophilic, but it's just not electrophilic enough. Okay? So in order to spiffy this up, you use pinch of sulfuric acid. The sulfuric acid protonates the OH as it would an alcohol. So you can think of nitric acid at this moment of an alcohol. Okay? And remember what happens with alcohols? You protonate OH, it turns into H2O as a good leaving group. The leaving group leaves, and you leave behind a carbocation. You do this for this guy, protonate, leaving group leaves, you get an N+, a so-called nitroniumine. And that's the hot intermediate that does the electrophilic aromatic substitution. Yeah?
Why isn't the negative oxygen
All right, that's a good point. And that's in the 7th edition now. We emphasized this several times, mechanism. When we write mechanisms, so we have a reaction, vocabulary, new reaction, and we do the grammar of the mechanism. For obvious reasons, we just write the mechanism that leads from starting material to product. But in the background are all the other reactions that you can possibly imagine that could occur, will occur. So, but they don't lead to product, and they're always reversible. Okay? If they weren't reversible, the reaction wouldn't happen the way it's described, right? So they're dead end streets. They all occur in the background. So in this case, to address your question specifically, that proton can protonate also these oxygens here, and it can protonate the sulfate of sulfuric acid. So anything that has an electron pair, these H pluses jump around like crazy. Okay? But that doesn't lead anywhere. It's just a lot of frantic activity with nothing to show for. Only when you protonate here do you make a species that then loses water and makes the reactive nitroniumine. By the way, here's a reminder of the color scheme and mechanisms, which I hope you'll find useful. All nucleophiles are red, all electrophiles are blue, leaving groups are green. And the function changes as the mechanism proceeds, right? So we got a nucleophilic oxygen being red, being hit by the blue H, that makes protonated water. And the next step, protonated OH, which is water. And the next step, the water is a leaving group, so it's green, okay? And it takes off, and then you get the blue N+. And that guy is the hot species. That now is a much hotter version of nitric acid. It's sort of like saying we have a haloalkane, which has an electrophilic carbon and a negatively polarized halide. We rip off the chlorine, then we have a carbocation. That's what we did here. We have a hydroxynitrogen, that's not hot enough. We rip off the OH as water, and now we have a nitrogen-based cation. You look at the electrostatic potential map, totally blue here because it's the plus charge. And then this undergoes electrophilic aromatic substitution. The electron pair attacks. You get this usual intermediate. There's the plus charge. The plus charge is not trapped by the negatively charged sulfate to make the addition product. Rather, this guy deprotonates to regenerate the aromaticity of nitrobenzene. I forgot to say something which I'm going to say here. Both in bromination and nitration, and in many electrophilic aromatic substitutions, they are also highly selective, meaning that the product, which of course also contains a benzene ring, does not compete with the starting material for the electrophile. And the reason is that both halogens, like bromine or chlorine, and nitro, and we'll see other groups, are electron withdrawing. And so they take electron density away from the product benzene ring, making this benzene ring less red, less electron rich, compared to starting material. So the electrophile, being faced with the menu of very red and a little less red will go for red. Okay? And so just by Coulomb's law, more electron density. So this guy will stop at the stage of mononitration, and in the previous reaction, the reaction will stop at the stage of monobromination. Okay? So here's case 3. That's sulfonation. And the reagent here now is one of these vicious brew type mixtures. It's SO3, sulfur trioxide, which in itself is a highly corrosive, highly vicious reagent, mixed with concentrated sulfuric acid, sometimes called fuming sulfuric acid. There are various names, oleic acid, and so forth. So that mixture is one of these mixtures that if you accidentally happen to lean on it, put your fist in it, you'll slowly sink in it because your fist will disappear. Sort of Boris Karloff type scenario. So SO3 looks like this. This is a valence shell expanded species. Incidentally, this was mentioned in the break. Valence shell expansion is possible for elements below the second row. Oops, here. Because the Lewis octet rule strictly applies only to the second row. But if you don't like valence shell expansion, this is a 2468.S8. You can write a dipolar structure with the octets. Okay? So you can stick to octets. And down here, you can ignore the one on the right, just stick to this. Okay? That's fine. Don't need to write these resonance forms. And this is mixed with consulfuric, and then you mix it with benzene, so at room temperature, bang, you get the electrophilic aromatic substitution product, where SO3 has attacked and displaced the proton. Since SO3 is neutral, when it gets attacked by the electron pair, it becomes negatively charged, so it gets protonated in the product. So this makes a benzene sulfonic acid, and it introduces sulfur. And this is useful for a variety of reasons. One is benzene sulfonic acid derivatives are part of a class of drugs called the sulfur drugs, so it's important in medicinal chemistry. It's also very important in synthetic organic methodology, as we shall see, because we can reverse this. If you take a benzene sulfonic acid and boil it up in dilute, in other words, water is the essential ingredient, aqueous acid, the SO3 will blow back out and you get back your benzene ring. Okay? So it's like, so we can reverse that reaction by the appropriate choice of reaction conditions. And the back reaction is driven by the enormous hydration energy of SO3. SO3 is basically anhydrous sulfuric acid. It's H2SO4 minus H2O gives you SO3. So making H2SO4 by hydration of SO3 is enormously exothermic. If you were to do it by just dumping SO3 into water, it would just blow in your face, okay, because it gets so hot. So it's like instant boiling. Okay? So one can drive this in both directions. How does this go? The electron pair attacks the very electrophilic sulfur, accentuated best perhaps in the octet structure, where we have 2 positive charges on this sulfur. So you attack like this, electron pair moves out. You got this what's called the zwitterine species, where you have both a positive charge and a negative charge, the dipolar form you can call it. And this deprotonates rapidly, most likely by a proton being plugged off by any one of these species here. And then the O- here is reprotonated externally to make the benzene sulfonic acid. There's a movie I want to show you. In that movie, it actually happens all at once, which is probably not accurate, but they did that to save space. But here it is. Here's the benzene ring, and SO3 comes in from the top. Here's the electrophilic sulfur, and it hits that carbon, and it forms the intermediate. That's now an sp3 hybridized carbon, and over there's a positive charge, but rather than attacking here, the proton comes off, and it protonates on the oxygen of the SO3. Now comes a class of electrophiles that are very useful for synthetic applications because they're carbon-carbon bond forming reactions. As you remember, in order to practice synthetic organic chemistry, we need to make carbon-carbon bonds because it's the art of making more complex carbon frames from less complex ones. And there are 2 reactions. They're both called Friedel-Crafts. They're both named after Friedel and Kraft, namely Charles Friedel, who worked at the Louis Pasteur Institute in Paris, and James Kraft, who was at MIT. So these are called Friedel-Crafts reactions. They're both alkylations or acylations. Okay? So an alkylation, we just use a haloalkane, and we replace H by R. This looks like a totally new reaction, but of course it isn't. Okay? Remember that we did essentially the same thing when we used Br2 or Cl2, except that R and X were the same, and they were both bromine or chlorine. Rx itself doesn't react with benzene. In fact, benzene is used as a solvent to dissolve haloalkanes. You have to, again, spiffy up the Rx unit by adding Lewis acid. And here, the Lewis acids that were invented or used by Friedel and Kraft were aluminum halides. So here again, if X is chlorine, you use aluminum trichloride. If X is bromine, you use aluminum tribromide. And all this thing does is the same thing it did in the bromination. It grabs the X and pulls it away from R, making R, that's already slightly blue, a lot more blue, sufficiently blue that it will attack and do the substitution. And that's the trick. So here's the mechanism, which is identical to what we just did here. Okay? But instead of another X, we have the alkyl group on the left. But here's the X that's activated with aluminum. You get this activated complex where this carbon now is strongly delta plus, and now it gets attacked by the double bond of benzene, kicks out the leaving group. Here we have the intermediate, plus charge here. Proton is plugged off again by X, so this is identical to this step here. Can you see my pointer? Probably not. This step here.